Alright, let's make the golden rectangle. I'll start with a circle, and using the same 2 points I used to define the original circle, I'll define a second circle. These 2 circles are the same size. They have the same radius. The distance between their centers is 1 unit. I'm going to make a few more circles just like them, using this intersection point and the distance to one of the other centers. I have now a third circle which is the same size. Using this intersection point and this center, I have a fourth circle that is the same size, using this intersection point and the distance to any of the other 2 centers that are reachable from there. I have now another circle that is the same size. I have 5 circles which are all the same size. They are all separated by 1 radius. I am going to take, let's see, these 2 circles, they're both of their intersection points, and draw a line across them. In Euclidean geometry, it requires only 2 points to define a line of indeterminate length. I'm going to do the same thing with the other 2 circles over here on this side. Now then, I have 1 horizontal unit there. I have the vertical units. I'm going to take the intersection point of these 2 circles, and I am going to enclose them. That also is 1 unit. Now I have my unit square created from 5 circles which are all the same size. I'm going to clean up my drawing. I'm going to remove these circles. I'm going to remove my vertical lines. I'm going to remove my dots that I don't really need. And I'm going to minimize the lines of my circles and copy my visual style. Alright. I have a square. I also have, since I've got 2 overlapping circles centered on each corner of the square so that they're the same distance apart, I have in this figure another place where I can draw another vertical line and cut that square in half. I will take this intersection point in the middle of the square, and I will clean up my drawing. Now, at this point, well, I don't know. I mean, I kind of, let's see here. I'm going to leave that for a second. I'm going to go ahead and take another intersection point right up there. Okay. And now I'm going to clean up my drawing by removing the vertical of indeterminate length. Now, at this point, I want to say that if I take a segment, if I take a length, that is that. And if I make that the radius of a new circle, it's going to be a different size from all of the circles that I've drawn up to this point. So there to there, that is my slightly larger circle, centered on the midpoint of the base of the square, with a radius, which is this section that I drew here. Okay? Now then, if I take this horizontal line and extend it until it meets that circle, and then if I do the same thing across the top, and if I draw a line perpendicular, and I'm just going to use the built-in for this, perpendicular line from point, and then I'm going to go ahead, I'm going to put another thing there. And at this point, I'm going to go ahead and clean up my drawing. So I'm going to remove, so I think I might have unhid something when I wanted to hide something. So let's see, let's hide that. I'm going to hide my indeterminate length horizontals, my indeterminate length verticals. Let's see, so I'm going to hide that. Seems I have a number of points stacked up there. Okay, so now I've got a rectangle. I am going to connect the dots and do this whole rectangle right here. All right. So that rectangle then is the golden rectangle. So I'm going to color it gold so you know what it is. Now it's made from a square on its left side and an extra little bit left over. I'm going to go ahead and unhide this circle again. And let's see, I think I'm going to copy the visual style from there to there. And I'm going to go ahead and make those invisible so that we've only got that one circle. Now, when you're drawing a figure like this with a ruler and compass, it's not always necessary to draw an entire circle. You can just draw a part of a circle called an arc. And I would like to do that right now. I'm going to just draw a little arc. And now I'm going to hide my original circle. Before I do, though, I'd just like to point out that as much as we extended the square by this extra little bit, as I call it, in order to make it into the golden rectangle, we could have done the same on the opposite side. You know, it seems a little bit arbitrary to do it on one side rather than another. Alright, I'm going to hide the big circle, and I'm going to go ahead and I'm going to connect these dots. So we've got this figure here. I'm going to make this line really, really fine. Maybe not completely, right? I'm going to make this line also a lot finer. Maybe just a little bit more visible than the other one. I'm even going to pull that one down a bit. I'll try to make the arc look a little bit more like it. See, I'm just, this is what I call cleaning up my drawing. I'm gonna reduce the impact of the points that make up the drawing here. All right. So now we can examine in a little bit more detail the golden rectangle. So our square is unit 1. If we then take the length of the rectangle, the long side from this corner to this corner, so here to here, that length is going to be, in terms of 1, it's going to be 1.618. Okay. In Greek, the Greek mathematicians called this phi. So this is a length, this is a number, this is a special number. You've heard perhaps of pi, which relates to how a circumference relates to its diameter, or to its radius, which, you know, I mean, it's just half the diameter. Well, this is phi, and this has significance in throughout mathematics in different ways. All right. One common way that the Greek mathematicians would analyze a rectangle is they like to draw a diagonal across it and then draw another line at 90 degrees to this diagonal running through a point. And we can run through this corner down here. So let's do that. There's a tool built into GeoGebra for that, but you could also do this with a ruler and compass. let's try it sort of ruler and compass method. Just to keep us on our toes so that we have some notion that we know what we're doing. All right, so there's a circle drawn from that corner point, so centered on that corner point. Now this circle then intersects this diagonal line at 2 points, and let's go ahead and mark those. So I'm going to zoom in here, look a little bit closer, and I'm going to mark those 2 points. So I'm going to put a point there and a point there. In this program, you can tell that these are intersection points because of the automatic color labeling. They come out gray so that you know that they are an intersection of 2 lines and not a point that is free to move. So they depend upon those lines, in a sense. All right. Having done that, I'm going to first, didn't mean to draw a point. I just wanted to select this line because I want to minimize it because it's going to get in the way. We've got a multi-part operation here that we're doing. Okay, so you want to draw another circle then from each of those intersection points. You want to go halfway. Now the first circle can be, of any length or any diameter, as long as it covers greater than half the distance between it and the next line. If you wanted to choose a point in the geometric figure that was there already, you'd simply choose to make it go all the way to the opposite point. That would be pretty easy. There's a compass tool here, which maintains its, allows you to measure distances, compare, distances against others. Compass, a circle or radius is a distance, It's your good way of saying all points, that are a certain distance from the point that I choose. Anyway, I'm going to go ahead and use the compass tool. I'm going to select this circle, and I'm going to draw another circle that's equal to it, centered over here on the opposite point. So I assert that these circles are center, and since GeoGebra is dynamic, if I take the point that defines the radius of the original circle and move it, you see that the other one moves along with it. So it's dynamic. They're in fact related, and they're equal. Okay, I'm going to draw a line now between those 2 points, and as you can see, it runs through the point at the circle, and this then operationally, that's a term from the philosophy of science. Operationally, we can see that this line is indeed exactly 90 degrees from the other line. Okay? Now, interestingly, it also seems to run through this point right here, which defines the difference between the original square that I extended in order to make this rectangle. So this diagonal is to the whole figure as the diagonal here. That is to say, we're going to have to cut this down a bit. Is to the extra bit that was added. And if you think about it, you'll realize that this relates to a property that we're going to explore about this, which is that you can cut the extra little bit into a square and an extra little bit, and that square will have the same relationship to the extra little bits, as the first square has to the golden rectangle that we made out of it. All right, I'm going to go ahead and clean up my drawings a little bit so we can see, and I assert that this is true, and we're going to run with it, that this diagonal simply can be drawn between the 2 corners of the extra little bit, which we helpfully already have points to define. All right, so let's just start hiding parts of the figure that we don't really need. So that, and that. And I think that'll clean it up substantially. We don't need this one either, so I'm just going to hide it. And I will draw a new diagonal from there to there. All right. Now, whoops. All right, so this line and this arc right here relate to the construction of the golden rectangle. Okay, that we take this distance and we sweep down an arc that is that same distance to align horizontal with the base, and that is how we construct the golden rectangle from the square. It also relates to, whoops, try that again. Okay, it also relates to the fact that that length, which is highlighted at the moment, is the square root of 5, or actually it's half the square root of 5. I keep doing the wrong thing. All right. Which is to say that if you took the original circles that everything was made out of, and if you took their radius as 1, then you could have where I made this this square out of the top part of the places where those circles overlapped, with its base as the radius between those first two circles. If I made a second square that went below that radius line, that middle line, then I would sort of fill up the area between two vertical diagonals, of those circles. Let's just let me just, instead of describing it, let me just show it to you. So let's see here. So so I'm talking about this circle and this circle. So I drew a square above them. I could equally well have drawn a square below them. So there. Now, if I had, if we continue this line from the center here all the way down, then what we would get would be, in terms of the radius, in terms of the base of the square being 1, the length of that line, that vertical from, that sort of diagonal there, that would be the square root of 5. So what we have in the construction line of the golden rectangle is half the square root of 5. And then we also have half the square, because that's drawn from the midpoint of the square. That diagonal line is drawn from the midpoint of the square. So we have half the square, or half the base of the square, half the length, the width of the square, whatever you want to call it. That would be half of 1. So it's 1 plus the square root of 5 divided by 2, or half of 1 and half of the square root of 5, and that gives you the length of the golden rectangle. And then its height in this orientation is 1. Its height is the same as the base of the square. It's the same as the unit that we made the square from. So that's how you get to phi, your 1.618, and so on, because it's also an irrational number, like pi, like the square root of 5. All right. So let's see, I'll just hide that and hide that. See, you can't really hide things too much when when the field is so full. So that's why I'll click on an object and just undo the show parameter Don't want to see that one. Don't want to see that one. And as right now, I don't really want to see the original two circles. And having explained the construction lines here, I don't really want to see them either. So I'm going to get rid of this. I mean, I'm not going to get rid of it permanently. I'm just going to make it not show up. Get rid of this one. I like seeing them, though. The construction lines that lead to this form. It pleases me to see them. But right now, I think we really want to analyze the form in terms of the diagonals. So we have one diagonal and we have another diagonal that's at 90 degrees to it. And we know that it's at 90 degrees because we use the procedure for drawing a perpendicular line from a point. Now we've got an intersection point right there. And we have a square, and that intersection point, I assert, will divide the extra little bit into a square and an extra little bit. Okay. And, oops. And then we have another situation here where we've got a diagonal. I mean, if you take just this part, this has the same proportions as the original figure. You've got two diagonals which run from one corner to the other and from one corner to somewhere on the edge. And that spot on the edge that it runs to, I will assert, will divide that remaining rectangle into a square and an extra little bit. And having done that, we are left with an area which I think has the same properties yet again. And can similarly be divided into a square and an extra little bit. And now we're left with essentially the same thing at a smaller scale. And so on, right? I mean, dividing things, I mean, think about it. When you do division, you're in that pattern where, you keep getting a remainder of 3, and you keep starting with the same number, and you just keep, remainder of 3.3, 3.33333, and you can see, that you're never going to get a different number, Dividing this thing is the same. You can see that, however many squares you take out of it using this procedure, you're never going to get to a point where you can't take any more squares out. This is just going to go on and on and on. And that's what makes it the golden rectangle, because it has these special properties, this special arrangement of the diagonals, these special situation with the squares and the extra little bit, which has the same proportion. Now, when I first learned about this some years ago, and I did a lot of looking stuff up about it, it seems that it relates to a lot of things. There is, it relates to some things in number theory. It relates to ideas about beauty. It, if you look for these patterns, patterns involving this kind of progression, there are a lot of them to be found in nature, which does, I'd say, make it seem like there might be something, a bit spooky about it, frankly, a bit, mysterium tremendum. It doesn't seem very easily explicable, at least not to me. I don't know what I'm missing, but there does seem to be something rather special about this. All right, so I've drawn an arc in the original square. And what I'm doing is I'm taking a corner, and I'm going to take this corner. You see that highlighted? And then I'm going to take the spot where the arc ends, right there at the bottom. And I'm going to take that as the start of my new arc. And then I'm going to draw another arc over here at the opposite corner. And it kind of seems like it matches up, doesn't it? I'm going to take sort of the corner in the middle there of the square just above, and then I'm going to continue the arc around. See, from here to there to there. Yay. And from there to there to there. Yay. And let's see, can I do the other one? No, I can't. I'm going to have to zoom in a little bit in order to do this one. So, from there to there to there. Yep. And let's see. Well, we know, we'll just make a point right there, right? And we'll draw one more arc, right? From here to there to somewhere over here. We could just stop right there, I think, for now. I've drawn one more arc, then I've drawn a square to contain it. If I had the square, then I would know where to put the endpoint, but I don't. And you see, my little endpoint is kind of blue. It's kind of free-floating. I'll just hide it. In fact, I'll hide the squares as well. And I'll hide some of the dots, because creating squares creates a lot of dots. So that is the golden rectangle, and that is the Fibonacci, or the golden spiral. Fibonacci spiral, I've seen it done as golden spiral. I've seen it done as golden because it relates to the golden rectangle. And I've got overlapping points on my corners, which is why I have to keep hiding them multiple times before they're actually hidden. And also why you see how, like, this little diamond-shaped one that I made earlier, I put those in all the corners, and now they're not showing up because they were selected first when I selected points on the corner to hide. The overlapping points, the ones that were put down, were somehow selected first. Okay, so this is an interesting spiral, and part of what's interesting about it is that it's made with an arc that is 90 degrees of a circle, okay? And yet it seems to flow together pretty smoothly. Each time you draw 90 degrees of arc, you're moving the center point, and then you're taking right back up the end point of the previous arc, and yet it seems to flow fairly smoothly. It's said to resemble a nautilus shell. I've watched mathematics lectures on video that have shown that there is in fact some slight difference between the rate of increase of the curve and the rate of increase of the curve of the nautilus shell. But it's a pretty close match. It's pretty good. You can also use this in composition. I'm an artist by training. I did not come from the math world. I didn't come from the technical world. I'm coming into the math world because I'm interested in it. Because largely I'm coming in because I feel like I should know it, and I feel like I don't know it, and I never knew it as well as I should have. And so I'm very curious about it. And so I'm sort of approaching it as an artist. I'm exploring it artistically. And that's kind of the whole reason why I'm using this program, is because I heard about this, these mathematical things that you could do, and I wanted to try and do them on the computer. I mean, you can also do this with a compass, and ruler, straight edge, paper, pencil, and I do have some of those. I've tried it out. It works pretty well. This is kind of the idealized version of that. It helps you to do it. The concepts. You don't have to have a lot of skill with your fingers. And then you can explore it, and you can go down as far as you want to, because you can zoom in. In the real world, when dealing with paper, you can't always, look at things as closely and keep going as far as you want. You can keep going as far as you want. The place where those two lines cross there, that's kind of the eye of the spiral. The spiral is always tending towards that point, but never reaching it. That's the definition of an asymptote. Always tending towards, but never reaching. It's about lines and points and curves. But there you go. In looking at this, I've been searching for images related to this for a while, and I've learned that there are different arrangements whereby you can make the same or a very similar spiral. There is such a thing as the golden triangle, which we might try to do. There is you can take the boxes that make up the golden rectangle. That I mean, you can do this sort of inside out. You don't come up with exactly the same angles, but you come up with angles that are so close, that it's amazing. What do I mean by that? Well, let's see. Let's just start fresh. So the basis of this is I'm going to use the built-in tool for drawing a square. Now, we started at the beginning of this video by doing a square, using Vesica Piscis, the overlapping circles. But that's, you don't, this does provide sort of a built-in template, so that you can skip all the underpainting, all the, All right, so you got two squares, and then you got a bigger square, which it would comprise, in terms of the smaller square, the bigger square would be 4 square units. If each of the smaller squares were 1 square unit, the big square would be 4 square units. 1, 2, 3, 4. 1 square at each corner. And you can keep going with this. You can make another square that fits onto those. And then you can just keep going, make another bigger square. So you can start from the inside and sort of go out, and if you sort of analyze this, you try to draw the same kind of diagonals, the same kind of midpoints, the same kind of arcs, you will get a very close approximation to the golden rectangle that we just drew, the other way, starting by, extending a unit square to, with half the square root of 5, and drawing its diagonals and using those to cut it down into smaller and smaller squares. So in this case, we built up squares rather than cutting down squares. It's like, 2, 4, and the number of units in terms of the smallest squares that we started with when we created this, the number of units that each square comprises and that the whole figure comprises as it increases is very close to, if not identical, with the Fibonacci sequence, which is one of the reasons why the spiral in the golden rectangle is probably identified with Fibonacci. So it has something to do with life. This is another interesting, thing. I mean, what is mathematics? Is it an abstraction? Is it a human invention? Is it a social construct, or are we really perceiving something in the fundamental structure of the universe? Like sort of a Neoplatonism or something like that. And it's spooky. It really is. It's amazing that when you look at some geometrical figures, they seem to relate to the patterns of life, and Fibonacci is very much about that. It's, it starts with a riddle about rabbits. If, the increase in rabbits, you start with 2, and from something like their second year, every so often they have so much increase, and I don't know how the riddle was originally posed, but the answer turns out to be a number sequence that you see embodied here and in many other things. If you count the spirals on a pine cone or a pineapple, or the seeds in the head of a sunflower, and there are many examples of living things that have such units of increase. You start with cells, and the cells divide and increase in number by doubling, and it's not exactly perfect. There's also this concept of harmonic numbers, and a lot of this is involved with architecture, and presumably, and I don't want to step on anybody's toes with this, but presumably some of this underlies some of the mysterious revelations in say the Freemasons. You think, well, what is a mason? A mason is somebody who builds something with bricks. And what do you have to know how to build something out of bricks? Well, you have to be able to count the right number of bricks, for one thing. You got to know what measurements you need to stack the bricks up high enough so that you can make a wall or a doorway that somebody can go through without bumping their head. And what is the basis of that in the ancient world? Well, it's geometry. So anything that seems special about geometry is going to be of tremendous significance to people who are in the business of building things out of bricks. And if you like to believe that there's any kind of special significance in what you do as a profession, as a means of earning a living, well, that's going to seem very important to you. And I'm not going to deny it. I mean, I say it's spooky. I'm like, having drawn these figures and done some dabbling with compass and straight edge, I really do feel the power of the idea that there is a very, interesting order, in the structure of the universe itself. So, let's see. Let's go about breaking this down. If we go across here, and then I'm going to use the perpendicular line tool here. So I'm going to draw from this corner a perpendicular line through there. And how about that? Even though I didn't make this the same way, it seems to go through the opposite corner in much the same way, right? How about if we did this differently? Let's go back a couple. So what if I did it across here? And see, because I'm going to try to make those lines line up where the squares diminish, because I did sort of construct them in a spiral pattern. Anyway, perpendicular line from this corner through that, or not that corner. How about through this? Whoops. How about through this corner, from this corner through this line? There we go. Okay, let's zoom in and see where it lands. So there you go. That's pretty good, huh? And if we drew a spiral from these squares, let's start on the outside, since well, I mean, that's the way it makes sense to do it to me. So let's try doing this by starting on the outside. Let's see. Boom, boom, boom. What did I do? Boom, boom, boom. Okay, great. No. Boom, boom, boom. Okay, let's try that again. All right. Boom, boom, boom. Yay. Okay. Boom, boom, boom. Boom, boom, boom. All right. I'm going to have to zoom in because there's a lot of dots there. All right. So, boom, boom, boom. Boom, boom, boom. Boom, boom. Oh, nope, 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 nope. All right. Let's zoom in some more. Boom, boom, boom. Boom, boom, boom. All right. And that's about as far as you can go. I don't know. Let's try one more. Yeah, so that one is different from all the other steps because that square is exactly the same size as the square that came before it. And therefore, what we're getting is not 90 degrees of arc, but 180 degrees. We're getting half a circle. So that's what you get there. Let's go ahead and I'm gonna get rid of the dots here. The dots are getting in the way of seeing what's going on here when we're zoomed out more than anything else. So I'm gonna hide some of the dots. All right, and there you go. Yes, I'm not selecting anything. There you go. All right, well, I'm going to cut this off. I hope you enjoyed it. Over and out.